All right, so today we're taking a look at section 5.4. I know that on Monday we just covered 5.1, but I wanted to jump to 5.4 because I think it's another place where we can sort of have a soft landing as we enter this very accelerated course, okay? So we're gonna be taking a look at right triangle trigonometry. And I do want to emphasize that we're looking specifically at right triangles, okay? At some point later on this semester, we're going to look at non-right triangles, and the rules are a little bit different. And so it's really important for us that we think about all of the things that we're going to do right now as specific to right triangles. So you've got to have that right angle, okay? So let's go ahead and get started right here with our Sokatoa. How many folks in this space have heard that phrase before? You can just put a 1 into the chat if you have, or a 0 if you have not. So 1 if you have heard Sokatoa before, 0 if you have not. There is no judgment either way, more just trying to get a gauge of where we're at. All right, so it seems like most folks have heard of Sokatoa before. And it's one of those things that, like, when people find out that I teach math, they're like, oh yeah, Sokatoa. Like, that's like one of the things that people say. And then I'm like, oh, you remember that? What does it mean? They're like, I don't know. It was just really fun to say. And so that's something that, like, I hope we can sort of at least develop a little bit more than, oh, I know that phrase. I would really like for us to know what that means, okay? And so I'm wondering if we can maybe start with this. And if someone could tell me what the SOH stands for. And again, you can type that into the chat, or you can unmute yourselves or send me a direct message. All of those options are fine. Yeah, nice. Okay, so not too rusty there, right? So the S in particular stands for sine. And so we usually abbreviate that S-I-N, but we don't say sin, we say sine, okay? So this is an abbreviation, we're just taking the first 3 letters. But sine is exactly this idea of opposite over hypotenuse, okay? But let's see, where do I want to write this? Okay, let's actually draw a diagram to kind of go with this before we write out the different trig names. All right. There are many things that I'm excited about for getting back into the classroom, but one of the things I really appreciate about teaching remote is that I feel like my notes are so much neater, and like my diagrams are not as terrible as when I freehand them on the board, because sometimes things are just, you know, you all saw my half circles on Monday. They're not great all the time, but like, you know, this app helps me draw straight lines here, and that's great. But okay, let's label this triangle. And one of the things to know when you're labeling a triangle is that each of the vertices, or sort of the corners, if you will, each of those get labeled with an uppercase letter. So if we use an uppercase letter, we are specifically talking about an angle. All right, so A, capital A, uppercase B, uppercase C. What we have here is triangle ABC, but the uppercase letters stand for the angles, okay? And so if I were to say sine of angle A, all right, I would want to look from angle A. It's almost like if I could move myself to angle A and look out and kind of see the triangle, okay? Now, one other thing to note is that when we label the sides of a triangle, we actually label them with lowercase letters, okay? And so if I have angle A here, and I go across the triangle, the side that is opposite A, we call little a. All right. So what does that make this side? What would I label this side? Yeah, I would label that little c. Now, unfortunately for us, lowercase c looks suspiciously like uppercase c. So just kind of try and make one bigger than the other. But that means that that last angle B, if we go straight across the triangle, that side we're going to call lowercase b. Okay, so using those letters, can someone tell me what the sine of angle A is? All right, so let's take a look. So we've got angle A, and the side that is opposite that is lowercase a. I know it's that autocorrect, right? Gets you every time. But this lowercase a is indeed the side that is opposite angle A, and the hypotenuse is lowercase c. Now, how did we know that lowercase c stands for the hypotenuse? That's also a really important question.
The hypotenuse is the longest angle, or the longest side, I mean.
Yeah, it is the longest side, and it's always opposite from wherever that right angle is. So if you know where the little square is to say this is a right angle, then opposite that side is going to be your hypotenuse, okay? All right, so we have sine of angle A. What's cosine of angle A? Yeah. Oh, how'd you avoid that autocorrect? Nice job with the lowercase b. So here's A. We have our side that is next to it, which is lowercase b. And we have the hypotenuse. That's great. Now, how did we know that? Might be a good question in case anybody's sitting here being like, where are people coming up with this? Well, the CAH, right? CAH, that stands for, and we'll write this down later, but C stands for cosine, A stands for adjacent, and then H stands for hypotenuse. All right, last one. What do we have for tangent A? If we wanted to use the letters that we have here to write a fraction, there we go. I agree, opposite over adjacent. Great. All right. Now, all of this, though, is specific to angle A. Okay. So I want to ask us a pretty classic question. And using the same diagram, I'd like us to find sine of B, cosine of B, and tangent of B. Okay. So this time, we're not looking from angle A, but we are looking from angle B. Right, we're going to use the same blue letters we have on our diagram, and whatever we might recall from Sokatoa way back in the day, and fill out these three, I don't know, let's call them ratios. When you think you have an answer, go ahead and pop that into the chat. Again, you can post it publicly. I think we are a very caring and understanding class. Mistakes are always welcome and encouraged. Ian, I understand what you're saying. And that's not quite right, but I'm also looking for us to just use the little blue letters from here. So maybe like scale it back a little bit, okay? We'll get to where you're going later next week. All right, so let's see. If we have angle B, the opposite side is lowercase b and the hypotenuse is c. So b over c. Okay, that looks good. Cosine of b is going to be the adjacent over the hypotenuse. So a over c, I agree with that. And then tangent is going to be opposite, which is b, over the adjacent, which is a. Nice. Okay. Now, for those of you who have seen right triangle trig before, this is definitely a review. If you've never seen this before, we're going to dive more deeply into this, so don't feel too overwhelmed, okay? All right, so really good warm up here. Let's write down some important things though, okay? And our goal here is we're going to be filling out this table throughout this week and next week. It's a really great table to keep in mind, like how the different names relate to each other, because we're going to be introducing a lot of functions and they all have different names. And instead of trying to memorize them as separate pieces, I thought it would be nice to be able to sort of compare and contrast what's the same and what's different about these. Okay, so we're going to start here with these main trig functions, and we'll spell these out for ourselves, right? So the first main trig function is sine, and it is spelled S-I-N-E. And what sine stands for is that the first three letters, S-I-N, that's just our abbreviation. So sine of theta, right? There's that Greek letter theta again. It's like a 0 with a horizontal line across it. Sine theta is defined as the ratio between the opposite side and the hypotenuse. All right. So somebody walks up to you on the street and is like, tell me what you know about sine. You're like, easy. It is the ratio between the opposite side and the hypotenuse side. That's it. Okay. Now, if we go back to our Sokatoa from earlier, the S comes for the sine. The O refers to the opposite, which is the top of the ratio. And then the H refers to the bottom of the ratio or the hypotenuse. Okay, so that's where we get the SOH from. All right, next up, cosine. All right, so same sort of idea. We abbreviate cosine by just grabbing the first three letters. And we've got cosine of theta is defined to be adjacent over hypotenuse. All right, and if we go back to our Sokatoa from the beginning, the C stands for cosine, A stands for adjacent, and H stands for hypotenuse. And last but not least, we have tangent. And just like sine and cosine, we abbreviate tangent with the first three letters. So tangent of theta equals opposite over hypotenuse. And that is our T. Oh, I wrote this wrong. This is supposed to be adjacent. TOA. Okay. So we have our Sokatoa, but what does it stand for? It stands for sine, cosine, and tangent. And what does that mean? Well, they're all just ratios of different sides in a right triangle. Okay. This idea is so important that I wrote it down here. All right, what do sine, cosine, and tangent really tell us, right? They are functions, that's true, all right? But in mathematics, sine is a trigonometric function of an angle, all right? The sine of an acute angle, all right, because we're only working in a right triangle, is this. It is the ratio of the length of the side opposite that angle to the length of the longest side of the triangle or the hypotenuse. Okay. And again, that is so important. I'm going to go ahead and highlight that for us, that for a specific angle, it is the ratio of the length of the side that is opposite that angle to the length of the longest side of the triangle, right? And that is in particular for sine. If someone asked you to explain what cosine or what tangent was, I bet you could go through this same definition and change a few words, right? But it gives you, especially for those of us who maybe feel like we don't always know how to say, you know, what we understand about the math, this is a really good example of how we could sort of grab a definition and change it for the different parts that we're looking for, okay? All right, let's talk a little bit more about some special triangles, all right? So I'm gonna start here with my little homemade drawings, all right? And in this first diagram, these are isosceles, right triangle, okay? What does isosceles mean? Someone answer that for us. Okay, two side lengths are the same, exactly. So when we're looking at these triangles, one thing that I do want us to notice is that we should put in some marks to make sure we know that two of the sides are the same, okay? So in particular, in this little pink triangle, this side and this side are the same length. Okay. And in the purple triangle, this side and this side are the same length. And in the blue triangle, this side and this side are the same length. Okay. All right, so let's fill in some numbers here. All right, let's say in this pink triangle that this side length is 2. How long is this side length? All right, that's also 2, right? If one side is marked as 2 and it has the same little hash mark as the other side, they're the same length, okay? Anybody happen to know the length of the hypotenuse? Or how could we find it? Ooh, root 8. I agree with that. Can you tell us how you found that? Nice. Yeah, great, great, great. Okay, so let's we won't do this for all of them, but let's do this just one time off to the side where we have a squared plus b squared equals c squared, okay? And we would plug in 2 for a and 2 for b, and c is what we're looking for. And so we get 8 equals c squared. And so Matthew is very correct in saying that c equals the square root of 8. And generally, if you have taken any length of class with me, you know I'm not super big on like simplifying, but for this example, I'm wondering if we can simplify this one more step. And I don't mean turn it into a decimal. Like, how can we rewrite this square root? Yeah, we could do 2 root 2, right? And just in case anybody's confused about how that happened, we could write 8 as 4 times 2. And then we could take the square root of 4 and we get 2 with the leftover square root of 2 inside. Okay. And so that means that we could label this third side as 2 root 2. Okay. Now, since we're here on this pink triangle, let's call this bottom corner here theta. All right. So I'm wondering if someone can tell me what is the sine of theta for this pink triangle? Good. Yep. We take our opposite side, which is 2. We put it over our hypotenuse, which is 2 root 2. Great. Okay. Let's reduce that. Right. And we have a 1 over root 2. Great. Okay. Tell me what I would write for cosine. Cosine of theta in the pink triangle. Okay, so cosine means we want the adjacent side, which is 2 over the hypotenuse. So 2 over 2 root 2, which we can reduce to 1 over root 2. Great. All right. And last but not least, we have our sine, we have our cosine. The third main trig function is tangent. And what 2 side lengths would we put in to the ratio to get Ian's very correct answer of 1? Good. Yes, we would put 2, which is the opposite, over the hypotenuse. Great. Okay. All right. Let's do this again with some different numbers. And this time, let's see if we can start to take a look at some patterns that are happening. Okay. So I'm going to tell you that this side length is 7. All right. What are the other side lengths of this purple triangle? Okay, I agree there's a 7. And like in the pink one, we had 2 and 2, and then we had 2 root 2. What do we think the hypotenuse could be here? Nice, it is. It is indeed 7 root 2. And I'll leave that for you to confirm if you go ahead and use the same Pythagorean identity that we used before. I bet once you simplify, you'll get 7 square root of 2. Okay. All right, let's take a look at the 3 main trig functions again. We'll put theta down here again. We've got sine theta, cosine theta, tangent theta, right? take a moment, fill those in the privacy of your own learning environment. And just like we did for the pink triangle, simplify where you can simplify, and then let's kind of see what we have, okay? Right. Nice. All right. So I know that this requires a lot more typing, and I appreciate your contributions here. But yeah, for sine, we're gonna have 7/7√2, which just like with the other one, the pink one, we could reduce, and we get 1/√2. Great. Okay. Cosine, we get 7/7√2. Again, that gets down to 1/√2 when we reduce. And for the last one, we end up with 7/7, which gives us 1 because we can reduce those. Perfect. Okay. So let's pause here for a moment, right? Because I have two triangles that are completely different sizes, right? One that I'm telling you has a side length of 2, 2 and 2√2, but then the purple one has 7, 7 and 7√2, right? So the side lengths are clearly different. What about our trig ratios? Are they the same or are they different?
Are they the same because it's like the same angle?
Ah, okay. That is what you just said is so important. I want to write that down. Let me find a good place to write it. Trig ratios are the same when the angles are the same. Okay. Trig ratios are the same when the angle measures are the same. Okay. Out of curiosity, does anyone know how big theta is in the pink triangle? Ah, that is correct. Yeah. Theta here is 45 degrees. Theta in the purple triangle is also 45 degrees. If this is also an isosceles right triangle and I call this theta, how big is theta in the blue triangle?
45.
Yeah, 45 degrees. Okay. So I'm not going to tell you how long the sides are in this triangle. But I want you to tell me what sine, cosine, and tangent are. So I claim that you already know based on what we have here. Okay. If I have a 45-degree angle, the sine of a 45-degree angle is 1/√2. It was true when it was the smaller triangle, but the angle was 45. And it was true for the bigger triangle when the angle was 45. So I don't know how much bigger the blue triangle is, but I know that the sine of that is going to reduce to 1/√2. Similarly, for a 45-degree angle, cosine is 1/√2. No matter how long the side lengths are, it really just matters how big the angle is. We can say that's 1/√2. And for the tangent one, tangent of 45 degrees is 1. Tangent of a different triangle with an angle of 45 degrees is 1. If I know the angle's 45, I know the tangent's going to be 1. So one of the things I really want us to take away from this particular exercise is that no matter how big or small the side lengths are in your triangle, what matters most is exactly what Ellie said. What matters most is the angle, the size of the angle. The size of the angle tells us about sine, cosine, and tangent. Okay. All right. I do want to try this again with a different special right triangle. Okay, so before we had an isosceles right triangle, but this time we're looking at what we call 30, 60, 90 triangles. Okay. And so looking at a sort of different category of special right triangles, and we're going to do the same exercise here where we have 3 triangles. They're all different sizes, but the angles inside the triangles are actually all the same. Okay. So let's start with the middle triangle this time. We've got this purple triangle right here. If this is a 30, 60, 90 triangle, let's go with this as our theta. Okay. And it turns out that, let's say the side opposite this theta, let's say it has a side length of, let's go with 5. Okay. And it turns out that the hypotenuse here is actually 10. I'm wondering if you can go ahead and find the side length that we don't know. All right, so take a moment, see if you can compute how long this side is. And just like we did over here, how Matthew had given an absolutely correct answer of square root of 8, but I encouraged us to reduce it more. All right, let's try and do the same thing, right? So whatever you get, try and reduce that so that you end up with something that has isn't just a square root. Okay. All right, we have 1/5√3. Let's wait for some other confirmation and kind of see. All right, I would agree. If you sit and work out the Pythagorean identity, all right, and let's actually do that. All right, so if I have a squared plus b squared equals c squared, where did folks put the different numbers? In other words, where did you put the 5 and where did you put the 10? Okay, so you said B equals 5, great, and C equals 10. Okay, and that is whether you put the 5 in for A or B really doesn't matter, but I cannot emphasize this enough. And I'm sure you've had teachers who've said the same thing. That 10 is the hypotenuse, that better be the C. It better be the one that is all by itself, okay? So we get 10 squared here. All right, so we get a squared plus 25 equals 100. A squared equals 75. And then when I take the square root of 75, I get, let's see, square root of 25 times 3, which gives me 5 root 3. Okay. And so this side on the bottom here would be 5 root 3. Okay. So we've got 10, 5, 5 root 3. Now let's go ahead and find our sine theta, our cosine theta, and our tangent theta. Right? So take a moment and do that. Plug in your numbers. If you can simplify, please simplify. I think we can for all of them in this case. So let's go ahead and do that simplification as well. I'll start to fill those in. And if you agree with what I have, go ahead and put a 1 into the chat. If you disagree, put in a 0. All right. Love a little positive reinforcement so early in the morning. Thank you for that. I'm glad we all agree with the work that we have here. All right, so any guesses as to how big theta is in this triangle? We know it's a 30, 60, 90 triangle, but is it 30 degrees? Is it 60 degrees? Is it 90 degrees? I see one vote for 30 degrees. I'd love to see other people's thoughts. Ah, okay. So I do actually really appreciate the answers in here. I think some of us sound like, okay, 30 it is, but some of us are like, well, it's definitely not 90, right? It's not 90, but like, how do we know? And I think it goes back to an idea that I know you all know, but sometimes we forget that is actually connected here. If you have the number 5, right, and that represents this side length, and if you have a calculator, maybe just type in 5 root 3 and tell me what decimal you get. Like, I really ask you to turn things into decimals, but go ahead and just turn that into a decimal for me, 5√3, and let's see what we get. Okay, 8.66, that's great. Okay, so if this 5√3 is about 8.66, then 5 is clearly the shortest side in the entire triangle, right? 5 is smaller than 8.66. Also, because I drew this in advance, I knew that this side, I drew it to be smaller than this side, right? What do we know about angles and sides? Like if I have an angle, so if angle A is bigger than angle B, what do we know about side A and side B? Right, there's a relationship between like angle measure and side measures, I think is important for us to highlight. No takers on that question? All right. So that is the response I was looking for. And it's possible that, that's not something that you've ever heard before. Okay. But if we have a side, or so if we have an angle that's bigger, we know the side opposite is bigger. We can actually say the opposite of that, which is if the side is shorter than a different side, then this angle is going to be smaller than the other angle. All right. So if we know it's choosing between 30 and 60, but it has to be the smaller one, then we know that theta is going to be 30 degrees in this case. Okay. So working on some reasoning here, but I think we're getting the point here. So I don't want to belabor the point too much, but I'm wondering if I tell you that this angle in the blue triangle is theta, and that theta, just like in the purple one, is 30 degrees, even though the blue triangle is bigger. And I'm not even going to tell you any of the side lengths. Can you tell me what sine, cosine, and tangent have to be for theta? Yeah, that is precisely the answer that I'm looking for, right? And probably a lot less work typing out your answer than trying to copy over those ratios, right? But if this angle is 30 and this one is 30, then the ratios of the sides are going to be the same, right? So we're going to have sine is going to be 1/2. Cosine is going to be √3/2. Tangent is going to be 1/√3. That's it. I don't even need to know how big the triangle is or how small the triangle is. As long as I know the angle measure, I know what the sine, cosine, and tangent are. Okay. So let's do one example before we take a break. Okay. So for example 1, it says for the given right triangle, label the adjacent side, opposite side, and hypotenuse for the indicated angle. Then find the 3 main trig functions for alpha. Okay. Now I'm trying to use as many sort of new letters as I can, but this alpha right here is another Greek letter. All right, so we've seen theta, now we're seeing alpha. All right, so maybe no one's told you yet, but you're about to find out that if you are doing math for any extended period of time, you're actually learning a lot of Greek as well. All right, because we're doing a lot of Greek letters all over the place. You'll become experts at many Greek letters. All right, so we've got this lowercase alpha. All right, and the way we draw it, I kind of think about like if I was drawing like goldfish in elementary school, it kind of looks like that. All right, and I'll draw it a few more times just so we can kind of see it. So it's like, if you know how to do infinity, it's also like 3/4 of infinity. You could think about it that way. All right, but everyone kind of finds the way that they like to write the letter. But I do want to point out that that is a Greek letter, and we often use Greek letters to talk about the angles here. All right, but if we look, we have this angle all the way down here. And the first task is I want you to tell me which side is the adjacent side, which side is the opposite side, which side is the hypotenuse, and let's actually write that out. Okay. So where should I put hypotenuse? Let's do the one that I think we all feel the most confident on first. Yeah, 17, right? 17 is the longest side, but also it's opposite that right triangle or right angle, right? So this we can say is the hypotenuse. Okay. Where is the side opposite alpha? Yeah, we start at alpha and we sort of look straight across that triangle. We get to 8. 8 is indeed the opposite side. All right. And that means that you only have one side left. By default, 15 has to be the adjacent side, right? But one way to think about adjacent, so the word adjacent means like next to, right? So it has to be next to the angle, but how come this side isn't the adjacent side? Because that's also next to the angle. It is too long, right? But that's also why I always label the hypotenuse first. Because if I start with adjacent, I might start with like, oh, I don't know, it's like one of two choices, and I don't know. But what I do know is that if I have the right angle, the side across from it is going to be the hypotenuse, right? So I almost do it intentionally as a process of elimination, so that I know that if I know my hypotenuse and I know my opposite, then the last thing I have is the adjacent side. Okay, so in case that's ever been confusing for you, you can kind of use that as a little like cheat code. If you type in your hypotenuse and your opposite first, then the last side has to be the adjacent. Okay. All right, so let's finish the problem. We're given 3 main trig functions. So that means we're asking for sine of alpha, cosine of alpha, and tangent of alpha. And the fact that I have the alpha here is so important. So important that I'm going to show you what I will not give you credit for if you write it this way. Okay, if you write this as your setup, then you've missed the whole point of trig functions. Okay, it is more than just being like, I didn't want to write the extra letter. It's like you changed what it meant. Okay. Remember that comment earlier that was so important that I wrote it down? Trig ratios are the same when the angles are the same. And trig functions are of an angle. So what did I do wrong in this red part that I wrote over here? I didn't even write the angle out. Okay, so do not use that as a shortcut. Okay, please, please, please write in whatever angle you have here. All right, exactly. There's no alpha symbol, no theta, no like X. There's no angle on that side. Okay. All right, what do we get for sine of alpha? All right, so let's go back to this actual question. What do we get for sine of alpha? How do we get 1/2? Never mind. I think it was an arithmetic error, or I'm not sure. But how do we get sine of alpha? Okay, so remember, sine is opposite over a hypotenuse, right? That is the purpose of Sokatoa, is to help us remember that. And so we're just going to take the opposite number, which is 8, and we're going to put it over the hypotenuse, which is 17. Okay. Okay, what's cosine? Which two numbers should I choose from here? Yeah, we're going to go with adjacent over hypotenuse, right? And maybe we write a little reminder for ourselves. This is opposite over hypotenuse. We have adjacent over hypotenuse. Our last one, tangent. We should have 8 over 15 because we're looking for opposite over adjacent. Okay. So I don't know if we're pretty quiet today because this is stuff that we're all, we've already seen before and it's not that different for us, but there are some really important fundamentals here that we're definitely going to keep using throughout the course. So I just want to make sure that we're like feeling really solid on this. Okay. So as promised, we're going to take a break. So it is 10:38 right now. I'm going to go ahead and pause the recording. So let's start with a diagram here. So if we have a right triangle, and we label, let's just mix things up a little bit just because, let's say I put theta up here. I'm wondering if you can tell me where I should label the hypotenuse. Let's start there. Where should I label the hypotenuse?
The one that's like not horizontal, diagonal.
Yeah, great. So we'll call this the hypotenuse. Great. All right, where should we label the opposite? At the bottom. Love it, love it. Okay, and that leaves adjacent to be the one that's on the right-hand side, right? Okay, so it doesn't really matter where our angle is, but everything is always in relation to this angle, okay? And I want to do a very quick review of the 3 main trig functions that we just talked about, right? So we talked about sine theta equals opposite over hypotenuse. we talked about cosine theta being adjacent over hypotenuse, and we talked about tangent theta being opposite over adjacent. Okay, those are things that we definitely want to know and love and know how to use. But what are these letters, right? And so we're going to actually figure out where these letters came from by taking a look at one very specific word here, the word reciprocal. Okay. So let's say someone walks up to you on the street and says, here, take a look at this, 1/2. What's the reciprocal? All right. And more specifically, maybe we would say, oh, the reciprocal is 2/1, right? Okay. And what if this person was like, okay, but what about -3/7? What's that reciprocal? Yeah, -7/3. Nice, nice. Okay, so the idea of the reciprocal, it's not that we're changing the sign, right? But rather we are taking the numerator and the denominator and we're flipping them. And so using that definition, what is the reciprocal of opposite over hypotenuse? If all I did was write the reciprocal of that, what would I write? Yeah, I would take the numerator and I would bring it down to the denominator, and I would take the denominator and I would move it to the numerator, right? That's all I did. I used the definition of reciprocal, and so I flipped the top and bottom, okay? Let's practice that definition a little bit more. What if I said, here's the adjacent and the hypotenuse. Find the reciprocal for me. You would tell me. Okay, because before I had adjacent on the top, but now it's adjacent on the bottom and hypotenuse on the top. Great. All right. Reciprocal of opposite over adjacent. Take that denominator, move it to the numerator, take the numerator, move it to the denominator. Perfect. Right. Now, before we add more words to this, can I just get everyone, and I would actually prefer that you send this to me directly, not to the whole group, but to me in a direct message. A 1, if this makes sense, like you understand where the reciprocals, like how we got the reciprocals, or a 0 if you're like, I don't know what we're talking about. Right. And again, this is a non-judgmental thing. It's simply because in the classroom, I can see things like eyebrows being like, what is happening? Or like blank faces or scared faces, right? But like in this platform, it's a little bit harder for me to see. All right, looks like we're all coming in mostly at 1s, which sounds good to me. If you have not yet responded, I'm going to assume maybe that you don't have a keyboard accessible or something, but your feedback is still important to me, okay? So we've got all these reciprocals. That's all we mean when we say reciprocal trig function. All we mean is we take what we defined one function as, and we flip-flop the top and bottom, and we get a different function. But now that we have a different function, we need to give it a different name. Okay, so life would be easy if this was reciprocal sine and reciprocal cosine and reciprocal tangent. But mathematicians didn't name it that way. Okay, so here are the names that go with the functions that we've just written. Okay, the reciprocal of sine is something we write as cosecant. The reciprocal of cosine we write as secant. And the reciprocal of tangent we call cotangent. Okay, those are just the names we're given. So sine, the reciprocal sine is cosecant. Cosine, its reciprocal, we named it secant. And tangent, that reciprocal, we named cotangent. Okay. All right, let's start with cotangent. What would you, if you were going to abbreviate cotangent to 3 letters, what would you write?
COT.
Exactly, right? So COT, theta stands for cotangent theta. All right, if you were going to abbreviate secant into 3 letters, what would you use? Great, SEC theta, right? We grab the first 3 letters. That's the rule we've been using for all of them. So let's just keep doing that. All right, what 3 letters would you choose for cosecant? Right? Now I see the answer in here, CSC, but maybe some of us would be like, I don't know, we've been grabbing the first 3 letters of all the other ones, so why wouldn't we use COS, right? Because the first 3 letters are COS, but that's already been taken, right? COS stands for cosine, so we can't use COS again here. And so for cosecant, we choose the C, the S, and the C. All right, so cosecant theta. All right. I know that it can be overwhelming to see all the different letters and all the different abbreviations. But if you know your Sokatoa, which it seems like most of us did in the beginning, all we're doing for these other 3 is flip-flopping the top and bottom and giving them new names. That's it. Okay. All right. So let's go back to a diagram. All right. Let's label some things and let's find some things. So for the given triangle, it says that let lowercase c be equal to 13 and lowercase b equals 5. Find the 3 main trig functions and the 3 reciprocal trig functions for angle B. And so let's go ahead and just highlight where we are looking from. And one of the things that I really like to do is set up my answer, right? So I know it's asking me for the 3 main trig functions. So I can automatically write out sine B equals some fraction, cosine B equals some fraction, tangent B equals some fraction. That's the 3 main ones, all right? And I know we just talked about these, but help me out. Give me the 3 reciprocal functions, starting with the reciprocal of sine. What's the reciprocal function of sine?
Cosecant.
Cosecant, good, good. So CSCB, great. All right, what is the reciprocal of cosine? Good, secant B. All right, what is the reciprocal of tangent? Good, cotangent B. All right, the more you say these words, the less scary they become, right? And the more you show yourself that like you earned this spot, you can say these words, you know what they mean, right? Embrace that part. This is some like grown-up stuff here that we're doing, right? All right, so I think given the information we have right now, we only know 2 of these 6 values. Which 2 do we know?
Like C and B, but like we
We
can
know
use
C
those
and
to
B.
find
Which one of 2 of the trig functions do we know? That's a better question.
we can use those to find the cosine and secant.
What makes you say cosine and secant?
Because you need the, oh wait, no, I mean sine and cosecant because you need the opposite and hypotenuse.
All right. Thank you for connecting those dots right there. So we have our angle B. Maybe one thing I should have done is written opposite down here, hypotenuse here, and adjacent here. So I would know which side is which, right? There is no shame in labeling your triangle like this, okay? It's not like it doesn't make you more or less good at math if that's what you have to do in order to get the correct answer here, okay? But I love the way that Ellie just talked us through that process because we do in fact have the opposite and the hypotenuse. So that gives us 5/13 for sine. And how did you know that cosecant was the one that you could find right away?
Because they use the same values as the sine in the, yeah, those are the ones we have.
Exactly. We use the same numbers because as fancy as cosecant looks, all it is you take sine and you flip the top and bottom. That's it. Okay. So yes, we all know Sokatoa, but if we know these, we know the reciprocal one. Okay. All right. You folks have been so on top of using that Pythagorean identity. I hope that's something that you're thinking already. That's how we're going to find A, right? So if we do a little work off to the side, A squared plus B squared equals C squared, and we get A squared plus 5 squared equals 13 squared. And we get, let's see, A squared plus 25 equals 169. I think that gives us A squared as 144, which means A equals 12. Okay, so we could do this the long way, plug it into the Pythagorean theorem. That will always work for us. Okay. And for those of us who are like, we like having sort of quote unquote nice numbers at our fingertips to use. The 3, 4, 5 triangle, that's a very special Pythagorean triple. As long as 5 is the hypotenuse and 3 is one of the sides, you automatically know the last side is 4. Okay, but this one right here, I picked it because 5, 12, 13 is another nice Pythagorean triple, right? So if you know it's a 5, 12, 13, you don't need to do that work, right? Look at how much ink you saved. But if you want to practice this for a bit until you convince yourself that you know the 5, 12, 13, awesome. Okay. All right. Knowing these, someone tell me cosine of B. What is cosine of B? Great. We're going to take the adjacent value, which is 12, and we're going to put that over the hypotenuse, 12 over 13. As soon as I write down cosine, look at the way I arranged my paper, right? This is on purpose. As soon as I know cosine, I know secant. 13 over 12. All right, for tangent, we need opposite, which is 5, over adjacent, which is 12. And as soon as I've written tangent, because I set my paper up cleverly, I know my cotangent, 12 over 5. Okay. So a nice sort of warm up into this idea that these three might have scarier names because we just don't use them as much, but the concept there is that they are the reciprocal trig functions. That's it. Okay. All right. Let's take a look at some juicier problems though, for better or for worse. All right. I think it's good to know some more like fundamental and straightforward problems, but sometimes the beauty in math is really around that problem solving. And so that's what we're going to take a look at in example 3 and 4. All right, so in example 3, assuming C is the right angle, solve the triangle with sine B equals 1 over root 3 and A equals 2. Okay. The first thing that I expect us all to do, that I encourage us all to do, is to draw a diagram. I am very suspicious of work that is done without diagrams, especially in trigonometry. Okay, so let's draw a diagram. Whoa. Okay, mark off that right angle, right? And this one we're going to label as C. Where do you want A and where do you want B? Okay, so let's go A at the bottom right and B will be the top left, right? And it doesn't matter. It doesn't matter. And so that's the thing that I think some people are really hesitant to draw a diagram because they're like, I don't know where to put the letters. Well, the good news is wherever you have to put a letter, you have to put that there. But if it's not specified, you have a little bit of wiggle room. If your diagram looks like this, but someone else has an A up here and a B up here, that's still okay. All right, that's still okay. All right, so let's see what information we have. Let's start off with this, this one right here, A equals 2, okay? So little a is 2. Where should I label the 2? I have 3 lines to choose from, a vertical one, a horizontal one, and a diagonal. Yeah, we're going to go with the vertical because little a is in fact across from capital A. All right. All right. I know little b is going to go down here. I know little c is going to go down here. It's going to go there. Okay. Let's unpack this other piece of information. Sine b equals 1 over root 3. All right. So sine b equals 1 over root 3. I know that sine means opposite over the hypotenuse. Okay. This is opposite side B or angle B. This is my hypotenuse, and this is my adjacent side. But here's the thing. I don't know that this is 1 and this is square root of 3. Okay. And here's why. Remember those pink and purple and blue triangles we took a look at earlier? And in all of them, we were able to reduce down and get the same value. Maybe before I reduced, this was like 2 over 2 root 3. I don't know, right? And if it were 2 over 2 root 3, that would mean this side is 2 and this is 2 root 3. It could have been 15 over 15 root 3. And that would make this side 15 and this one 15 root 3. But I hope we can see that there's a problem because we don't know if this is the original form or if this is a reduced form. Okay. So here's what we can do. All right. We can call little b 1x. If we call little b 1x, what should we call little c? In other words, what would I put down here so that when I reduce the fraction, I get 1 over root 3? Yeah, exactly. If I put x square root of 3, the x's will reduce and I'll get to 1 over root 3. So x root 3. Okay. Here's what that allows us to do. This allows us to go back to our friend a squared plus b squared equals c squared and fill in some information. So we have 2 squared plus 1x squared equals x square root of 3 squared. All right, let's simplify. What does 2 squared give us? Four. Good. What does 1x squared give us? Yeah, 1x times 1x gives me x squared. Good. What about that right-hand side? Great, right? And we could write that as 3x squared. Okay. All right. I want to solve for x. What can I do?
Can you subtract 3x squared and then minus x squared?
I could, yeah, for sure. And so that would give me, which way do you want to subtract? Do you want to subtract the x squared or do you want to subtract 3x squared?
3x squared minus x squared.
Okay, so we'll get 4 equals 2x squared. Great, what do we do from here? Divide by 2. And last step. Yeah. Okay. Now, I want to pause for a moment because I think that there are some of us sitting in this space that are maybe wondering, well, how would I even know to do this? Okay. That's partially why we're going over the examples. It's not just like, okay, when you see this, you're going to do this, but I really want to introduce us to a lot of different strategies so that as we're looking at these problems and when we study in particular, we want to study, how do I know when to use what? Okay. In fact, that question is so important. I want to type that into the chat. How do I know when to use what? All right. Anytime you are studying for things for this class or really for any class, that is a question you want to make sure you know how to answer. All right. A lot of times when we're doing this in lecture together, I tell you like, okay, what about this? What should we do next? 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 Right. And I'm fine doing that in lecture. And when we get to an exam, sometimes what makes the exam hard is we're used to someone else asking us those questions. And so if we're not in a place where we can answer these questions ourselves, I think that's really that line of like, am I ready for this exam or not? Okay. And so it would be really important for us as we study to make sure that we are independently able to answer questions sort of like this. Okay. Okay, well, we found X, but what does it mean to solve a triangle? We didn't even really talk about what it means to solve a triangle, okay? So in this case, what we're looking for is we want to find all the sides of the triangle, okay? Solve the triangle, find all sides. At some point later, it might become find sides and angles, but right now we're just trying to find sides. Okay. Well, we already know one side. We know 2. A is 2. We were given that. What's B?
I feel like what we did earlier, it's root 2, but visually, I feel like that doesn't make any sense.
It is root 2. It is root 2. And are you saying that because this side is shorter than this side?
Yes.
Yes. Okay. And that is absolutely valid. That is absolutely valid. So one of the things that I do want to say is that like not all diagrams will be drawn to scale, right? And so it's good to be questioning that and saying like, listen, AC is definitely not as long as BC is, but in the diagram, it looks deceiving, right? That is okay to be skeptical about that. But yes, we know that B is X, but we found X, right? So that means that we found B. And if we know B, I argue that we can also find C. What does C give us? Yeah, we would do square root of 2 times square root of 3. And this would give you square root of 6. Okay. And so we have solved our triangle by finding the 3 sides there. Okay. I would go back over this part of the process along with this part of the process, because I think that's really where the concept part goes. All right. But while we're here, let's try a different one, right? I think the more we kind of try these, the more we're like, okay, I kind of get the idea here. And you'll have a chance to practice these on your quiz as well. So Example 4, assuming C is the right angle, solve the triangle with tangent A equals 5/12 and B equals 6. And so I'm even going to lay this out in terms of like, what should we start with? And I encourage you to always start with draw and label a diagram. Okay. And so let's draw ourselves a right triangle. It can be any which way we want. It's definitely not a right angle, but I'm going to put a little square in there so I know it is. I know C is the right angle. It does not matter where I put A and B. I can do that wherever I want. So I'm going to put A up here and I'm going to put B up here. Right. And Dallas, that's part of the issue that we sort of ran into earlier is I randomly marked these as A and B. So again, that can be something that's scary for people. They're like, I don't know which side is longer. So how am I supposed to label the triangle? It's okay. You're just providing a sketch. It doesn't have to be accurate, but it should help you figure out some of those sides, right? So it's okay if at the end you're like, ooh, I realized that that diagram wasn't entirely accurate. I would make this side longer or this side shorter. That's okay. All right, so we've got this here and we have little b is 6. So I'm going to go ahead and write that in here. I know this is little a and I know this is little c. And with the information given here, which one of the 3 sides should I label as the opposite side? So A, B, or C, which one is the opposite side? Yeah, little a is going to be the opposite side. Exactly. So I'm going to put an opposite. I know this is the hypotenuse. This last one has to be the adjacent. Okay. All right. So we've got these 3 sides here. Now let's go ahead and take a look at that tangent piece and let's unpack that. Okay. So all right, so tangent A equals 5/12. I could put 5 here and I could put 12, oh, sorry, I could put 5 here and I could put 12 here, but what else could I put here? What would be another possible answer?
I think it's one of those special triangles that you talked about earlier. I don't remember the links.
Okay, well, let's just think about like how we reason through the sine B up here. I'm asking us to do the same thing down here, right?
Oh, okay.
Yeah, it would have been easier to see if we were like live in the classroom and you could see more than one board at the same time, right? But if we had over here, we said that this was like 1/√3 and we were thinking about the unreduced versions. Let's think about some unreduced versions down here, okay?
So we could put A over 6.
Be more concrete. Literally, what's another fraction that could reduce to 5/12? Okay, 10/24 option. Great. What else? What else could reduce to 5/12? Yep, 15 over 36, right? All of these are possible answers, and there's even more, right? We could keep multiplying and get a bunch of different answers. But the issue here is that we don't know which one. And so that's when we say, okay, let's just call it 5x and 12x, because I don't know what ratio I multiplied by. Okay. This is the reasoning that I'm looking for right here, right? You don't have to write all the little ones in between, but to understand why 5 over 12 can be expressed as 5x over 12x, that is important. Okay. And once you find that, we can find x. All right. So if we can find x, that'll help us find all the other side lengths. All right. And we might even say this: x is a scaling factor. All right. X is a scaling factor. That is how big or small is the triangle. All right. We're going to set up the Pythagorean theorem with this scaling factor. All right. And let's just kind of see what we have here. A, we can say is 5x. B, we can say is 12x. All right. So in the last problem, we used Pythagorean theorem, and we said a squared plus b squared equals c squared. And we plugged in the things we had. So 5x squared plus 12x squared equals c squared. Given this, can I find x? Like, can I find a number for x right now? Why not?
Because we don't know what C is.
Yeah, we don't know what c is, right? So let me sort of zoom in a little bit here. In the last question, we set up this ratio, and then we use Pythagorean theorem. Great. Can you do that for all questions? Okay, because this is where a lot of times we get ourselves into trouble. We're like, well, I studied one problem and I did it this way, so I must be able to do that for every single one. But look at what happens when we try it down here. It didn't work. So we have to have another strategy. Okay. And this is where I need you to really focus that energy on, like, okay, how do I know when to use what? Right. And if one strategy doesn't work, do I have a backup one to help me out? Why am I putting a red circle around this part right here?
Because you could probably do 6 equals 12x.
Exactly, right? In this case, they're both equal to b, right? 6 is b and 12x is b. And so if we do a little bit of arithmetic, we will see that, as Angel says, or as Ian says, x equals 1/2. Okay, we divide the 12 to both sides, 6 over 12 gets us to 1/2. So we found our x value. But to solve the triangle, we need to find the other sides. Right? So now that we have a value for x, right? Which letter can we find, or which side can we find, right? We know b, what can we find? Yeah, we can find a, right? We have a equals 5x. So a equals 5x, which means a equals 5 times 1/2, or 5/2. Right, we have a equals 5/2. I have a, I have b is 6. How do I find the third side?
Now you can do the Pythagorean theorem.
And now we can go back to our Pythagorean theorem. And now I think we have enough information, right? We have 5/2 squared plus 6 squared equals c squared. And yes, I'm intentionally working with fractions here, okay? I'm working with fractions because it is a valuable skill to have, all right? And the more we say, oh, let me just type that into the calculator, the less opportunity we give ourselves to practice that. 5/2 squared as a fraction, what does that give us? Good, we square the top, we square the bottom, plus 36 equals c squared. All right, 25/4 plus, let's see, let's get a common denominator here. 36 times 4 is 144. I add these together, I get 169/4 equals c squared. This is where I want us to practice that sort of mental arithmetic. How do I take the square root of 169/4? That seems like kind of a big number. Yeah, all we're going to do is take the square root of the top and the square root of the bottom. Square root of 4 is 2. Square root of 169 is 13. All right, so we've got our A, our B, and our C. And so we found all the sides of the triangle. Okay. All right. I know these classes are long. Let's take another break. Let's take a 5-minute break here just to kind of stretch our legs a little bit. Let's be back at 11:41. Okay, so take a quick break. The last stuff that we're doing here is also important. So I do want to make sure we get to it, but that we're all like in a space where our brains are able to absorb things. Okay, so I'll see you folks back here in 5 minutes. All right, so we've talked so far about the 3 main trig functions, the 3 reciprocal trig functions, and now we're going to get into this idea of identities. And so we have these 2 triangles, all right? And what I want us to think about is some, like a review of some of the stuff that we just talked about, okay? So for, let's see, how should we do this? So let's say for alpha, all right? So alpha being down here in this diagram, and let's call this a little a, b little b, c little c, all right? if I asked you to find the sine, the sine of alpha, you would tell me what over what?
A over C.
Perfect. A over C. Great. All right. And once you have that, you could say cosecant of alpha is C over A. Right? All right. Cosine of alpha. What do we get for cosine of alpha? Great, we get a B over C. And as soon as we know cosine, we know secant of alpha equals C over B. Great. And then tangent of alpha, what do we get for tangent of alpha? Good, A over B. And as soon as we have tangent, we have cotangent as B over A. Okay. Now I know that we don't know any of the side lengths, but we can still write the ratios, right? And so we're going to do the same thing over here in this other triangle. I'm going to label this A, little b, C, little a, big B, little c. But this time I'm going to say, let's take a look at angle beta. Okay, so beta, another Greek letter. Looks like that. Looks like a B, like a regular B, but with a little tail at the bottom. Okay, so for beta, let's go ahead and fill in all of these. All right, so as I'm writing these, folks, if you could just type in what sine of beta, cosine beta, and tangent beta are, that would be extremely helpful. Right, collective effort to answer this question. All right, so you can either send that to me as a direct message, you can send that to the whole chat, but let's find sine of beta, cosine of beta, and tangent of beta. You can also unmute yourself if you're like, I don't want to type anymore today. Yes. All right. So sine of beta is indeed B over C. And thanks to that contribution, we know that we have cosecant as C over B. Great. All right. Looks like Ian put a bunch in there. Cosine of beta is indeed A over C, which means secant is C over A, and tangent is in fact B over A, and cotangent would be A over B. Great. All right. Thanks for playing along, folks. Okay, so we've got our alpha and our beta. And I want us to notice a few things, right? And so this is actually, when I ask us to sort of notice things or observe things, for some of us that comes really naturally and we're like, oh, I totally know what she's going to ask, right? And for some of us, we're like, I don't know how someone saw that. That's all okay. No matter where you are on the spectrum, that is all okay. But the purpose of this is to help develop that framework, right? So if you just sit there and you're like passively observing, you lose out on that opportunity to just see whether your thinking was right or not, okay? All right. As mathematicians, one of the things that we are often called to do is to find patterns. And so I'm wondering, in looking at all of these letters here, can someone tell me one thing that they notice about the values on this side and the values on this side. And it could be a specific example. It could be a greater pattern, whatever comes to your mind. Either go ahead and type something into the chat. Again, it could be direct message or all the way to the whole group, or you unmute yourselves. So many options. But what pattern or patterns do we see right now? C is in the same place for both cases. I agree, right? So C, whoops, C, 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 C is the same as these four. That's a great observation. All right, someone else said the A's and B's switch. So like this is an A and then this is a B. Is that what that person meant? Yeah. So wherever there's an A, now there's a B. Okay, cool. What else do we see? These are all awesome observations. Oh, so this tangent is actually the reciprocal of that tangent. That's interesting. Yeah, I would agree they are, right? A over B is the reciprocal of B over A. What else do we see? Swapping the A's and B's, yeah. Let's look at this one. Sine alpha equals A over C. Is A over C anywhere else in this table? Yeah, A over C is sine of alpha, but it's also cosine of beta. Nice. And someone else mentioned that cotangent and cotangent of alpha and beta are also reciprocals. For sure. Let's actually stick with this cotangent alpha down here. I like this one. So cotangent alpha equals B over A. Do we see B over A anywhere else in this table?
Tangent beta.
Yeah, we don't see it on this side, but as soon as we peek over to the other side, oh my gosh, yeah, we see another B over A. So let me kind of start color coding some of this, okay? So we saw cotangent alpha equals B over A. And we also saw it on the other side of the table, that tangent of beta equals B over A. Okay. Let's see. We also saw that sine of alpha equals A over C. And we saw that also here, cosine of beta equals A over C. Can someone find a third pair where something on the left is the same ratio as something on the right?
The tangent of A and B is the same as the cotangent of beta of A and B.
Yeah. I know that's a lot to say. You could say tangent of alpha equals cotangent of beta. That would be okay. All right. All right, let's see. Dallas says cosine of the left is the same as the sine of the right. So cosine of alpha is the same as sine of beta. All right. Any other pairs that we're seeing? I see two more, right? This cosecant of alpha and secant of beta. Yep. And let's just double check those last two. Secant of alpha. Oh yeah, that's the same as cosecant of beta. Right? So I love the patterns that we found earlier. All of those that you mentioned are mathematically valid. And I think sometimes when someone asks us such an open-ended question, what do you see? And you don't see the thing that they want you to see, we can feel like, wow, I totally missed the boat here. But all those observations are actually very, very important for things that we're going to see later. Okay, so if your particular pattern wasn't something that we followed here, that's okay. It doesn't mean it's wrong. It means that maybe for a different context, it's going to be better. Okay. All right, so we filled in this table, and by filled in, I mean we actually constructed it. We made all of this based on what we know about sine, cosine, tangent, cosecant, secant, and cotangent. And then we looked and we saw some pattern. Okay. So before we write down the patterns, I want us to go back to just the pictures for a little bit. Okay. And humor me here. How big is angle C?
90 degrees.
Yeah, angle C is 90 degrees, right? Angle C is 90 degrees. And we know that because it has that little square in the corner, right? So we know that's the marking for 90 degrees. Okay, now let's play a little what if, okay? What if alpha is 40 degrees? How big is beta? How did you get that? You're right. How did you get that?
A triangle equals 180 degrees.
Yeah, triangle equals 180 degrees. If one of the angles is 90, what do the other two have to add to? 90, exactly, right? So if one is 40, the other one's 50. Okay, let's keep playing that game. Now, let's say that this is 30 degrees down here. How big is beta? Yeah. 90 minus 30 gives me 60. Perfect. Okay, let's do an example over here. What if this is 15 degrees for alpha? How big is beta? $75 degrees, right? Exactly. So here's another pattern that sort of secretly we've been talking about, okay? If C equals 90 degrees, then alpha plus beta equals 90 degrees. Okay. That means that alpha and beta are a special type of angle pairs. Alpha and beta are complementary angles. Okay. Complementary angles help us talk about the co-function identity. Okay. Complementary angles help us talk about co-function identity. The C and the O in the beginning here, right? So complementary co-function. Okay, they both start with the letter CO. That's actually going to be helpful in thinking about these co-function identities that we're going to talk about. So an identity just means something that's always true. Okay. So let's look at our table here for a moment. Sine alpha is equal to cosine beta. All right, so let's write that down. Sine alpha equals cosine beta. But keep in mind, we said alpha plus beta equals 90 degrees. So knowing that, what's a different way that I can write beta? If I know that alpha plus beta equals 90, what's another way that I can express beta?
Beta equals 90 minus alpha.
Beautiful. Beta equals 90 minus alpha. Great. So I'm going to use this substitution. I'm not going to say that that's the wrong color. I'm not going to say that sine alpha equals cosine beta. I'm going to change that to say sine alpha equals cosine, but instead of beta, I'm going to put 90 minus alpha. Does everybody see that substitution I just made? Everywhere I see beta, I'm just going to put 90 minus alpha. Okay. This, my friends, you have found a co-function identity. In words, here's what it means. Sine of some angle is equal to the cosine of the complementary angle. Sine and cosine are co-functions. Sine and cosine are co-functions. Sine and cosine are co-functions. That means sine of some angle, alpha, is equal to the cosine of the complementary angle, or like the angle that I add to alpha to get 90. As a quick review of Monday, how could I write this co-function identity for radians? Nice, nice. The only change we have to make for radians is sine alpha equals cosine of pi over 2 minus x. All right. Oftentimes you will see this in your textbook, pi over 2 over minus x. We don't really see it with the 90 degrees, but it still goes back to that idea of a co-function, complementary angles. Okay. Let's pick the purple one, the cosecant and the secant. Okay. So secant alpha equals cosecant beta. Another way I could write that is secant alpha equals cosecant 90 minus alpha. And let's put a box around this. This is a co-function identity. It's another co-function identity. So we have sine and cosine go together. Secant and cosecant go together. What do you think is one more co-function identity? Nice. So tangent of alpha, what could we say tangent of alpha is equal to? Good, cotangent beta, which we found from our chart above, but now we add in the complementary angle part and we get tangent alpha equals cotangent 90 minus beta. All right. So these three are co-function identities, but here's how we use them. Okay, we're going to use these in a lot of different ways, but here's how we're going to start to use them. Okay. All right. So without a calculator, I'm telling you that sine of 54 degrees equals cosine of x. And I want us to find x. All right. What's another way that I could write sine of 54? 54 is like my alpha now, right? Maybe we can get this on one page. Yeah. We said sine of alpha equals cosine of beta. And then we wrote it like this. So if I have sine of 54, how can I write the other side of that identity?
Cosine 54 minus x.
Not quite, not quite. Yeah, we want to have the one that we add to it to make 90, right? The whole idea, like the CO in front of everything, complementary, co-functions, that is really important because we want this to equal the cosine of the complementary angle. Okay. And so if we do the subtraction, we can see this equals cosine of 36 degrees. And so what does that mean x equals? Well, cosine of x, cosine of 36. This means that x equals 36 degrees. Okay, so that is one way that we can make use of this co-function identity. Now, I know we sort of went about this in a very roundabout way. So I want to share my screen real quick. I'm going to show Desmos on my screen real quick. So let me, where did it go? There we go. Okay. All right. So here we go. Desmos, definitely our best friends if we haven't found out yet. But before we start working with the things, I want to bring our attention to this little wrench in the right-hand corner where it says graph settings, right? So we're going to click on graph settings. One of the things that is 100% necessary to check is what mode you are in, right? And so right here, there's a few different things you can choose from. If you are like me and you are maybe older and your eyesight is not as good as it used to, you could make things definitely a little bit more intense, right? You could also do a reverse contrast for those of us who like the nighttime mode. I just found out about this recently. That's pretty cool. There's a Braille mode as well, where you can type in, like, well, I guess you would be typing in on a different platform, but where you could actually do this through Braille, which is pretty cool. And a few other settings that we'll play around with later on in this course. But the one I really want us to focus on right now is the one that says radians and degrees on the bottom. You see how radians is highlighted right now? If I want to check my answers right now, I have to go ahead and click degrees so that it'll give me, I'll be working in the right mode. Okay, so I've changed this to degrees. Now let me type in this sine of 54. Gives me a number, right? 0.809, blah, 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 blah. Let's type in our answer, cosine of 36. Bam, same answer. That means those are equivalent. Okay. We'll come back to this after we do the second example, because I think it'll be good to think about like what we need to change to make sure our calculators are working the way we want them to. All right, so second example, or example 6 for the day, cosecant of pi over 3 equals secant of x. So secant and cosecant are co-functions. So I could write this as cosecant of pi over 3 equals secant of, do I want to put a 90 here? No, but instead we should actually use what you suggested earlier, Dallas, which is pi over 2, right? So we're going to have pi over 2 minus x. Great. Okay. So, sorry, not minus x, minus the pi over 3, right? Our complementary angles. All right, let's do a little mental math here. Pi over 2 minus pi over 3. Believe that gives us pi over 6. Okay. And so right now what we're suggesting is that our answer is pi over 6. Okay, so let's, after we've done this work, go back and check Desmos to make sure we've got the right answer, right? So I'm going to go ahead and stop sharing this. I'm going to go ahead and start sharing the Desmos screen again. All right, so if I start typing in right now, cosecant, and I type in pi, I can literally type in the letter pi, it turns into pi over 3. Okay. And now I'm going to type in secant, so SEC of pi over 6. I mean, Desmos says we're wrong. But I claim that we're right. What's wrong with Desmos? How come Desmos, well, Desmos is not a math teacher, right? And as with any technology, though, that we use, the technology is only as useful as we know how to make it useful, right? Such a classic mistake. Here's what I did. I was in degrees. I was in degrees for the last question. But if I'm in a new question and it's in radians and I don't tell Desmos or my calculator otherwise, it's not going to be helpful for me. All we need to do, click radians, check out our last 2 lines here. Right now we have that cosecant of pi over 3 is equal to secant of pi over 6. Okay, such a small thing, but I share this with you so that if you get an answer that you know is correct, and you try and check it on a calculator, you try and check it on Desmos, and that technology platform tells you you're wrong, don't panic, go back and ask yourself, did I tell that technology everything it needed to know? Because if I didn't go back and clarify, I'm in radians now, we're in a different measuring land, then it's not gonna do what you need it to do, okay? But with a simple click of a button, now we're in radians, now our answers work out, and we're all fine and good, okay?
I have a question.
For sure.
Why do you use X, or if instead of X, like say for the first one, it's sine alpha equals cosine 90 degrees minus, could I use beta instead of X? I guess I'm kind of curious as to why we're using the X if we're just plugging in the angle.
Right. So yes, X in this case is like our beta, and 54 is like our alpha.
Okay.
Okay. Yeah. I think, as we'll learn with many things math, it's actually more about the structure rather than the specific letter we use. So we could put omega and tau in here, or any other Greek letter we wanted, but this concept would still be the same. If we're in degrees, we want to do 90 minus that other angle. But if we're in radians, we want to do pi over 2 minus that angle. Okay. Super good question, though. All right, my friends, we're going to finish off today with, I think, some questions that are a little bit more of what we're used to when we think about right triangle trig, okay? But if this was something that you're like, ooh, that's the one thing I didn't really get from lecture today, I would encourage you to go back, come to office hours, go to tutoring, read up on about it, whatever you find helpful, to say, okay, I really understand every concept that we've gone through, because we're going to come back and see these again. And so I don't want it to be like triggering in the sense that you're like, ooh, I didn't get that the first time, and now we have to do more stuff with it. I want to be very upfront with you that we're going to use everything again. Okay. So with that being said, let's be kind to ourselves as we finish off this Wednesday lecture. Let's talk about some applications of right triangle trigonometry. Okay. So classic word problems that we're going to be taking a look at. So example 7 says we have a 20-foot ladder leans against a building so that the angle between the ground and the ladder is 65 degrees. How high does the ladder reach up the side of the building, and how far is the bottom of the ladder from the wall? And so, like we did before, we are going to start with draw and label a diagram. All right. Go-to move for us, draw and label a diagram. And we make a few assumptions here. We assume that the ground or the wall and the ground meet at 90 degrees. I know this is not true of all buildings, but we hope that this is as structurally sound as as we want it to be, that things haven't settled too much. It's not like a really old building that it's still, the ground is meeting the wall at 90 degrees, okay? And now we've got a ladder, and the ladder is leaning against the wall. And so it might look something like this, okay? So we have the ladder here. This is a diagram, but notice I said draw and label a diagram. Like, I need us to interpret the information and then put it in the right places in the diagram, okay? So let's start with the first number we see, 20. Where do I put the 20? And what does it represent? Yeah, 20 represents the hypotenuse. Love it. Because the ladder is 20 feet long, and this is the ladder, right? It's not as cute. Like I know some people draw like the actual ladder like that, right? I'm not big into spending that much time on my diagrams. I appreciate it when other people do, but you have no pressure to do that. We just want to make sure the numbers are in the right place more than anything else, okay? Where's the 65 degrees go? Bottom right. All right, 65 degrees. Nice. And the reason we know that is because the angle between the ground and the ladder, right? So if we put the 65 up here, that would be like, oh, maybe we didn't read the question carefully, right? That we thought it said between the ladder and the wall, but it said the ground and the ladder. Okay, so there's two parts to the question, but let's take a look at the first part first. It says, how high does the ladder reach up the side of the building? Now, just like I'm not super creative with my diagrams, like this is the side that I want to find, right? How high does the ladder reach up the side of the building? This is in the vertical direction, so I'm going to call it Y. I know that's so boring, okay? But it's basically just saying the distance from the ground to the top of the ladder. And if we look at the second part of the question, how far is the bottom of the ladder from the wall? I'm going to be equally boring and say this distance down here is X, okay? You can label it A and B, whatever you want. I'm just explaining my reasoning behind my not so creative lettering, okay? So I've created a diagram, and more importantly, I've labeled the diagram. So to find Y, pick a trig function. All right. So to find Y, we're going to pick a trig function. And I'm going to redraw that triangle very quickly. Close enough. Okay. So we know that this is Y, this is what we want to find. This is 20, and this is 65. Should we use sine, cosine, or tangent? Let's go back to the acronym that we started with. Sokatoa. Which one is going to serve us best here? All right, so we got a cosine one, and tell me why you're choosing cosine. All right, we have the hypotenuse, I agree with you. And explain to me how Y is adjacent to 65.
The opposite is, so next to it is 65. It's not like opposite to Y.
Oh, okay. So you're saying that this is the hypotenuse, and where's opposite from 65? Like the up and down side or the side to side one?
Oh, wait. Oh, I thought Y was like more down and that's why it was next. Y.
Okay. So if we think about 65, maybe it would have been helpful if we had labeled opposite before we got started, right? Sometimes in the question, it's hard to think like which one is which. So if it's helpful to you, you can almost label that here. So you've already done that pre-thinking, okay? But now that we have opposite and hypotenuse, I think maybe sine would be a better function to choose based on that. Okay. And here's what we have. If we choose sine, the very first line I want you to write is this. Sine theta equals opposite over hypotenuse. Remember what a big deal I made out of you better have an angle there? We've come to the moment in the lesson where it's going to be so important that we have that letter there. Okay. Let's plug in what we can plug in. What numbers can I fill in and where should I fill them in?
You can fill in the theta and then also the hypotenuse.
Perfect. So we're going to say sine 65 degrees equals y over 20, right? We fill in all the information we have from that triangle. Before you bust out your calculators, explain to me how you can isolate y.
Multiply by 20.
Perfect. Y equals 20 times sine 65 degrees. If I ask you for an exact answer, or I don't say, or I say this is like a non-calculator question, go ahead and leave your answer like this, okay? I want us to write this part out and then type that into the calculator. Okay, if you start turning things into decimals earlier, you're going to end up with an answer that's not quite exact. All right, so I want us to do the manipulation first and then at the very end put things into the calculator. But if you type this into the calculator, you should get 18.126 feet. All right. All right. Now to finish this problem though, we need to find a value for x. Right? We need to find a value for x. What are people's ideas on how we could find x?
Now that we have the opposite, we could do cotangent or tangent.
We could do tangent for sure. I love this. Okay. And I see a different idea in the chat too. So I want to make sure that we take a look at both of those. So to find x, we could pick a trig function, just like we did in part 2, right? And let me just draw a quick diagram for that. We've got x and 20 and 65 degrees. This is my hypotenuse. This is my adjacent. Which trig function would we pick if we wanted to use this strategy? Yeah, we would choose cosine, right? We would say cosine theta equals adjacent over hypotenuse. We would fill in our numbers just like we did here, and we would wait until the very end to turn things into a decimal. But Omar has an equally valid method. If we know two sides of a right triangle, can't we just use Pythagorean theorem? And he would be absolutely correct. Okay, you can 100% do that. In fact, let's kind of set this up. If we wanted to use or a squared plus b squared equals c squared. If we wanted to use this, maybe we have x squared plus y squared equals 20 squared. And since we have y, we could plug that into this y, and then we could find x, right? I'm going to leave this for you to finish on your own time. I claim that in both versions, you'll get the same answer. Okay. And what I really appreciated about this, and Omar, I don't know if you did this on purpose or it just happened to be this way, but you know, this whole time I've been talking about choices and how sometimes we are forced to use one method. And sometimes the deeper we get into the problem, the more choices we have. And so I love how clever Omar was like, we've used this a lot today, a squared plus b squared equals c squared. Maybe we could use it again. And they are 100% right. And if you're like, I actually want to practice working with the trig functions more, this is a great place to work as well. Okay, so keep in mind, sometimes you have choices, sometimes you have, your hand is forced a little bit to be that way. Okay. All right. So I know that this has been a chock full day of a lot of content. So I'm going to leave this last example for you to kind of practice on your own. I think it actually brings up a really great point that as you're looking at these kinds of questions to kind of think about. If you try this one and you're like, I'm not really sure how to set it up, or I think I got this as my answer, you're welcome to either message me on Canvas or send me an email, or maybe most efficiently send me a message on Discord, and then I can check it and say like, yes, this is in the right direction, or no, maybe try something different. Okay. So I am definitely available outside of class time. And if you reach out, I would be more than happy to help clarify any things that you're feeling a little stuck on. Okay. So we're going to stop here today. I'm going to go ahead and stop